Today, we want to continue looking at limits. We're going to evaluate some limits given in a style that we're not familiar with, we haven't worked with yet. We've only worked with limits on graphs. We have our intuitive understanding of what a limit is. We want to think about where is the function headed? What is the function getting close to as x is approaching c? We also have the precise definition of a limit, which, while cool, is not really all that helpful. So the most important part is our intuitive understanding of a limit and our ability to figure out what a limit is, our ability to calculate a limit. But we do want to think a little bit about the definition of a limit. And let's start with these two problems. So in the first function, I have 2x squared minus x minus 1 over x minus 1. I want to evaluate the limit at the only interesting place there would be to evaluate a limit, where the function is not defined. If the function was continuous everywhere, all we'd have to do is plug in the value that we're interested in. The problem here is we can't plug in 1, so we have to do something else. Earlier, someone mentioned that something else. We can cancel out the x minus 1 because we noticed that the numerator is factorable. After I wrote these problems down, I wasn't even sure why I decided I was going to make you factor them, but here we are. So the numerator is factorable. And in problems of this type, we should be suspicious that we're in a math class and there's this denominator of x minus 1 that's making things very inconvenient for us. Man, I sure would like to plug in 1, but that stupid denominator is getting in the way. But then, oh, look, we found out that the numerator has a factor of x minus 1. It's kind of like a Scooby-Doo mystery. It's like in a Scooby-Doo mystery, there's like the Scooby Gang and 2 other people. One of them will be like the sheriff, who will look like Batman in a sheriff's outfit. And then the other one will look like some variation of Snidely Whiplash. And you're like, oh, I wonder who's impersonating the ghost here. It's like the economy of characters tells you who it is. You know what I mean? So we knew we could predict that x minus 1 was going to be a factor because I'm going to want to cancel it and say this is equal to 2x plus 1, so long as x is not equal to 1. So I can cancel the x minus 1 everywhere except when x is equal to 1. The expression still has to be undefined. Fortunately for our heroes, we don't care what's going on at 1. With a limit, we care about what's going on near 1. So let's plug 1 into 2x plus 1, and we get 3. I should say that with more confidence. We get 3, right? Yeah, okay. I'm not good at arithmetic, so we plug in 1 into 2x minus 1, and the limit is 3. Little algebraic sleight of hand. This is a super contrived problem. Don't think, oh, when I'm an engineer at Lockheed Martin, I know I'm going to be doing this a lot. You won't. This is just for illustrative purposes. The same thing happens over in our g of x. There's this x minus 2. That's what's causing our problem. We can't just plug in the 2. So we're going to rely on a little bit of algebra. This is a blue problem. And notice we can factor an x squared out of the numerator, and that will conveniently leave behind an x minus 2, which will be subject to canceling. So we can simplify g of x to x squared so long as x is not equal to 2. So I should make a note of that. But since we're calculating a limit near 2, we don't care about what's going on at 2. We care about what's going on near 2. And so we're just going to plug in the 2 into our simplified expression. Any questions? Yes. So when we cancel out a factor from a rational function like this, what we are seeing, if the denominator completely cancels out, that indicates there's a hole in the graph at that point. It just takes out 1 point. A denominator like in a rational function, a denominator that doesn't get canceled, that leaves a vertical asymptote. But if that denominator completely cancels out and leaves behind a polynomial, then we just get a hole in the graph at that point. And we can see that happen if we switch over to the graph. Oops. So that red graph, oh man, I even matched the colors correctly. I like it when it looks like I know what I'm doing. Maintains the illusion. So we have 2x squared minus x minus 1 over x minus 1. And that's producing a line. That line is just 2x plus 1. If I try to trace this over to 1, so if I trace along, oh, there it is. We see that hole in the graph. So we can't see it here because it's too small. But if I try to click on the graph when x is equal to 1, it tells me undefined. But since that x minus 1 cancels out, that leaves a hole in the graph and not a vertical asymptote. So factors that cancel out produce holes in the graph. So factor cancels out, hole in graph. And when I say cancel out completely. If it's an x minus 1 squared, only one factor of x minus 1 cancels out. That still leaves a vertical asymptote. So because we cancel out to a polynomial, that polynomial is continuous everywhere. So you can just figure out where the hole was. And for the other one, when we simplified, we ended up with a parabola. And so there's our parabola x squared. But there's a hole in this graph. We can't see it because it's too small. But if we try to trace over here to 2, we get undefined. So there's the hole in the graph. But I can't just like click there. Desmos is like, oh, I'm not getting in trouble for dividing by 0. So I'm not going to let you just click on an undefined spot. So even though these functions weren't continuous at the points we're interested in, they were continuous enough. It's just that 1 point that's missing. We didn't get a hole, or we got a hole. We didn't get an entire asymptote messing everything up. Any questions? So the short version is, if you can plug in the value, just plug in the value. However, if we can't plug in the value, just plug in the value. If we couldn't simplify, then we would just plug in stuff near the value. For that, we would also like to bring a machine on board. And actually, let me go back. If we couldn't just plug in the value, we want to plug in values near the point we care about. And we did that. We plugged in a bunch of values because that's all a graph is. This graph just shows us a bunch of values plugged into that function. And we can see, if we start tracing along the function, we can see as x gets closer to 2, my y is getting closer to 4. I can't go at 2, we get undefined, but near 2, we get stuff close to 4. And this is coming from both sides. Any questions? The second part of the question, how close must x be to 2 to assure that f of x is within 0.1 of, in this case, it'll be 4. So here, we're playing with the idea of definition of a limit. The definition of a limit says, the limit as x approaches c of f of x equals L, if and only if, for every epsilon, for every positive epsilon, there is a positive delta, such that x being within delta units of c implies f of x is within epsilon units of L. This 0.1 is going to be our epsilon. And we're trying to figure out what the delta needs to be to make sure that f of x is within 0.1 of 4. Or, oh, actually, I said f of x, it should be g of x. So we want to figure out how close does x have to be to 1 so that f of x is between 2.9 and 3.1. Now we could do this mechanically because we like that. I want f of x to be within less than 3.1, but bigger than 2.9. So that's 0.1 above and below. I want f of x to land in that window. And we want to think about how close does x need to be to 1. And for this, we could set up f of x and then start simplifying things, or we could do the best method ever, the only one that we ever really need, which is guess and check. That's how science works. Science is all just guess and check. One of the reasons that science is kind of frustrating, because you have to be prepared to be wrong a lot. So we're going to use the very technical method of guess and check. So what if x is, let's say, oops. Let's say x is 0.9. How close is that going to get f of x? So let's see, 2 times 0.9 plus 1. Oh, that's not within 0.1 of 3. So if I go 0.95, oops. 2 times 0.95 plus 1. Oh, there we go. If x is 0.95, that is 0.05 units away from 1, then f of x will be within 0.1 of 3. So it looks like on the bottom end, with our fancy guessing and checking, if x is at the low end 0.95, we'll end up at 2.9, which is 0.1 of 3. It's not within 0.1 of 3, but it's the edge. So we'll just have to be strictly close, greater than 0.95. On the other side, we could probably guess what's going to happen because we're just dealing with a line. And it looks like the line has a slope of 2. So if I want to be within 0.1, my slope says I should be 0.5. So context gives us some help here. But let's check. If I do 2 times 1.05 plus 1, I'll be at 3.1. So it makes sense. Our slope of 2 has helped us out, and it's the same on both sides. So in terms of the definition of a limit, for an epsilon of 0.1, our delta is 0.05. If x is within 5/100ths of 1, then f of x will be within 1/10 of 3. Looking at this closer, this makes sense. We're dealing with, when we simplify it, a linear function with a slope of 2. So whatever y change, however much y changes, x will change by half the amount. So this tracks with the slope of 2. So we're thinking this makes sense with the slope 2. It's important to point out, just one sec, sorry. I just totally went out of order. It's important to note at this point, we have the important piece of information. The limit as x approaches 1 of f of x is 3. We're done. We've got the important stuff down. We understand conceptually, this means that this graph is headed towards 3 as x is headed towards 1. We know everything that we need to know. And this is just trying to illustrate, this second part is just trying to illustrate the epsilon delta portion of the definition. That's all we're doing. So don't expect like a quiz to show up where I'm like asking you delta epsilon questions or epsilon delta questions. That's just making things precise. What's more important is our intuition about what's going on. Understanding the epsilon delta definition of a proof and being able to talk about it and explain it and see it in practice only matters when you become a math teacher and you happen to be teaching calculus. At which point you need to understand that you don't really need to explain this to a room full of future engineers. Question? So I looked at how far off of 1, the 1.05 and the 0.95. Yes. It makes sense that which part? So when I talked about the slope equaling 2, I'm only referring to the simplified form. So in the simplified form, we have the 2x plus 1, so we have a slope of 2. Let's talk about why the slope of 2 tells us that it's going to be 1/2. Our delta is going to be 1/2 of our epsilon. So to do that, let's draw a picture of our graph. So here's our 2x plus 1. I want, oh, and the whole happens at 3. So let's make a note of that. There's 3 in the middle. I want the graph, I want the y coordinates to be between 2.9 and 3.1. So I'm going to draw those on my graph. So down at, I want the low end of a 3.1. Oh, upside down. 3.-1 at the bottom. I want f of x to land between 2.9 and 3.1. So if I drop these intersections down to the x-axis, I know the limit at 3 is equal to, this happens when x is equal to 1. If I drop these limits down, they ended up at, this is the 1.05 and this is the 0.95. So if we go from 3, so at this point 1.3 to the point 1.05, 3.1, the delta y was a 0.1. And so since the slope is 2, the delta x has to be 0.5. So here's our slope of 2 from this point oops, I wrote it backwards. So because we have a line with a slope of 2, if our delta y is 0.1, that means our delta x is going to have to be 0.05 because our slope is 2. So the slope is delta y over delta x 2. So if our delta y is 0.1, like we want, our delta x is going to have to be half of that. So it's going to be the 1 over the 0.05. I only get to point this out because when we simplified this, we ended up with a linear function that had a slope. In the next one, we're not going to be able to make this argument. We're not going to just be able to look for a ratio because what's left over is an x squared. So it's going to be steeper on one side than it is on the other. So that's why we're not going to be able to do that on the second one. Yes. Correct. What's close enough on one side might not be close enough on the other because of the square. In this case, everything was nice and even because we had a linear function, so that kept things nice and even. Let's see what happens over here. And we're going to do the same thing. We're just going to plug in some values until we are within 0.1 of 4. But what we want to happen is that g of x to be less than 4.1 and greater than 3.9. And we're going to activate guess and check. So this one's going to work differently because instead of simplifying and getting a linear function, nice and predictable and simple, we're going to simplify and we end up with an x squared. So I'm going to be plugging stuff into x squared. Super high-tech style. I'm just going to worry about x squared. How close do I have to be? Let's try a 10th. I'm guessing, and now I'm going to check. I'm going to try, if I plug in, let's say 2.1 and square it, that is too far away. That's like 0.4 away. Too much. So what if I cut that in half? So like 2.05 squared. So I've gone to from a delta of 0.1, too big. That's for an epsilon of 0.41 to a delta of 0.05. I square it. 4.2, better. So I'm just going to keep cutting this down. Oops, not 4. 2, I'm going to try 0.01. No, I'm not going to go 4. I'm just going to start cutting down my delta until I get one that works. Now, this is not, this didn't land exactly on 4.1, but I didn't want to land exactly on 4.1. I just need to be less than 4.1. So now I see that a delta of 0.02 will work. So 2.02 squared is 4.08, and that fits. That's within spec. So 2.02 squared is 4.08, and that's less than 4.1. But that's on the right side. On the right side, 0.02 will work. We should check if that's going to work on the left side. I'm not going to worry about anything bigger than 0.02 because I have to bring it in small. So I'm going to just start with 0.02 and see if that works on the other side. So I'm going to grab 1.98 and square it. And that's 3.92. And that is bigger than 3.90. This is not the biggest delta that we can get away with. But we don't need the biggest delta that we can get away with. That's not what the definition requires. The definition says for every epsilon greater than 0, there is delta greater than 0. Here's a delta greater than 0. If you chose delta equals 0.01, that would also be fine. For a tolerance of 0.1, a delta of 0.01 will also get us within 1 unit. So if I did 1.99 squared, that's closer to 4 than 3.9. And if I did 2.01 squared, that's also within tolerance. We could go and figure out what the precise value of the precise maximum value of delta is, but it doesn't matter. The definition just says, is there a delta that we can use? And the answer is, yeah. Any questions? This is why epsilon delta is terrible for like a test question. Because if I have a tolerance of 0.1, then you're like, oh, 1 times 10 to the negative 15. If you know that the limit exists, then if you like, just pick a really small number. In this particular problem, because we ended up with a square, observing that to be within 0.1, we should probably be within 0.01, just because it's squares and stuff. Any questions? For every epsilon greater than 0, there is delta greater than 0, such that the absolute value of x minus t less than delta implies absolute value of f of x minus L is less than epsilon. How do I write which? To write it out, if you want a fancy math writings, you could say limit that was my purple pen saying, are we really going to do this? And I'm like, well, heck yeah, purple pen. I'm not an engineer anymore. I was an engineering student for like 2 years, and then I became a mathematician. And then the purple pen was like, oh no, you're becoming a mathematician? I'm like, oh yeah. So I'm not going to be doing anything useful? I'm like, oh no, we're not building stuff. Stuff has to work when you build it and you're an engineer. I'm a mathematician. The lab just takes place in my head. Nothing ever has to work. It just has to work in theory. That was the big draw. Because I couldn't make physics experiments work, but I could make math experiments for it. The limit as x approaches c of f of x equals L, if and only if for every epsilon greater than 0, there exists delta greater than 0, such that that one's a little bit iffy. Absolute x minus c less than delta implies absolute f of x minus L is less than epsilon. Using as many math abbreviations as I can possibly muster. Make things look complicated. That's what wizards do. So the symbols in play, I with the 2 F's after it is a fairly common abbreviation for if and only if. The upside down A is for all or for every. Epsilon greater than 0. The backwards E is there is or there exists. Delta greater than 0. The backwards epsilon is not as common. Sometimes I see such that written out, but when I was a student, my teacher wrote the backwards epsilon looking thing for. So this we read as such that. Absolute x minus c less than delta. Every when the difference between x and c is less than delta, absolute value says on both sides. Everything within delta units of c, and the arrow in this case would be read as implies. Let's now write the definition of a limit and make it look fancy. How's everybody okay? All the engineers are like, oh, no, but doesn't matter. 3 and 4. We've had the answers for so long. Why do you keep talking, mathematician? Why don't you give it a rest? So the important part of this problem, it's really important to notice that the important part of this problem for our understanding happened up here when we came up with 3 and 4 and how we came up with 3 and 4. In this case, we were able to use our fancy algebra skills, right? We've got all this algebra knowledge, we want to use it. But we really could have just started plugging stuff in to our function and seeing where the function is headed. Because the function is just a graph written some other way. It's just the values. The graph is just the values plugged in. Is everybody okay? Is everybody okay? Because I'm like, oh, don't worry about definition of a limit. That's just if you want to look fancy. Write that on your notebook and people are like, oh, it's math. Keep the engineers away. All right, that's going to do it for today. I will see you all on tomorrow when we'll concern ourselves maybe with some more practical matters. Everybody have a good day. Thanks for playing.